everyone, welcome back to the channel. So today in this video lecture we're going to be solving this problem, number of ways to arrive at destination. So this is yet another problem in the Dijkstra algorithm series. So basically you're in a city that consists of n intersections and they are numbered from 0 to n minus 1. That means you have a graph of n nodes and the nodes are numbered from 0 to n minus 1 with bidirectional roads between some intersections. That means there are bidirectional edges between those nodes. The inputs are generated such that you can reach any intersection from any other intersection, that there is at most one road between any two intersections. That means take any two intersections, we can always reach from one of the intersections to the other intersection. Okay, now you're given an integer array, 2D array roads which represents these edges, these bidirectional edges. Each of these edges has some weight associated with them, which represents the time which a person or an object takes to travel from one node to another node. Also, you are given an integer n, which represents the number of those nodes that we have. So what do we want to do is, we want to know in how many ways we can travel from intersection 0, that is node number 0, to node number n minus 1 in shortest amount of time. Fine. So because there are multiple ways to arrive at the destination node n minus 1th node in the shortest amount of time. So we want to count those ways, those paths which takes the shortest amount of time to travel from node number 0 to node number n minus 1, and that's all we have to return. The answer may be very large, so we have to output it, return it modulo 10 raised to the power 9 plus 7. So let's better understand the problem statement using an example. So let's take this example. Here we have 7 nodes which are numbered from 0 to 6. So 7 nodes numbered from 0 to 6. Now we want to find the various paths which starts at node number 0 and ends at node number 6. Consider only those paths which takes the shortest amount of time to travel from 0 to 6. So let's explore various paths. One of the paths would be just move from 0 to 6 along this bidirectional road, which takes a time of 7 units. So just move from 0 to 6. The time would be 7 units for this case. Another path is move from 0 to 4, then from 4 to 6, and the sum would be 5 plus 2, that is 7. 7 unit is the time. Travel from 0 to 6 along this path, that is move from 0 to 1, then from 1 to 3, finally from 3 to 6. This takes in the time of 2 plus 3, 5 plus 3, 8 units. Take another path, move from 0 to 1, then from 1 to 3, then from 3 to 5, and finally from 5 to 6. This takes in the time of 2 plus 3 plus 1, that is 6 plus 1, 7. One more path, move from 0 to 1, from 1 to 2, from 2 to 5, and from 5 to 6. Now moving from 5 to 6 is optimal, then moving from 5 to 3 and from 3 to 6. So we take this path. This do not add an extra shortest path, we just take this road to move to node number 6. So the time would be, for this case, would be 2 plus 3 plus 1 plus 1, that is 5 plus 1, 6 plus 1, 7. So these are the various paths that we have here. Now you can see that now these are the shortest path that we can have. All other paths that we explore will take time longer than this, the times that we have enlisted here. So out of these we can see that the shortest time is taken along this path, this, and this. So how many paths do I have along which the shortest time is taken. There are 4 such paths. First one is just move from 0 to 6. The second is move from 0 to 4, then from 4 to 6. Third one is move from 0 to 1, then from 1 to 3, 3 to 5, and from 5 to 6. Fourth is move from 0 to 1, 1 to 2, 2 to 5, and from 5 to 6. So there are 4 total paths. Now, so the answer is 4 for this test case. So how can I solve this problem? What is the strategy to solve this problem? Let's see that. Now, it's simple. We want to find the number of possible shortest path from node number 0 to node number 6. That's the problem statement. Fine. Now, we know how to find the shortest path. Just use Dijkstra algorithm to find the shortest path distance to move from 0 to 6. And while we execute the Dijkstra algorithm, we keep track of the number of ways to arrive at any node of the graph in a separate array. Let's call it ways. So we'll take 2 arrays. The first one is the usual distance array. The second array is ways array. What is ways array? This calculates the number of ways to reach at any node of the given graph containing 6 nodes. So let's take a priority queue as we do usually in Dijkstra algorithm. So in the priority queue, push the source vertex 0 along with its distance, that is 0. Now pop out the top node, run the usual while loop that we do in the Dijkstra algorithm. Pop this node from the queue. So we have node number 0 and its distance is 0. Now traverse its adjacent nodes, node 4, 6 and 1, and update the distance for these nodes. We can see that. So first of all, we know that this distance array is initialized with very large number, while the distance for source node will be initialized to 0, and this ways array is initialized to 0, while this node number 0 is initialized to 1. Why? Because we know that ways to reach the source node, that is node number 0, is always 1. There's only one way to reach this node, that is just start from that node. Now traverse the adjacent nodes, node number 4, 6 and 1. And for node number 4, the distance that the updated distance would be, we can see that the distance for the parent node 0 is 0. So 0 plus 5 is 5. Is 5 better than the distance that we already have for node number 4? Yes, because already we store infinity. So we store 5 for node number 4. While we see the number of ways that we already have in this node number 4. We can see that we are visiting this node very first time. So we are visiting this node first time. That means whatever the number of nodes the parent node for node number 4 has will be the number of nodes for this node as well, because we are visiting it for the first time. That means the number of ways to visit node number 4 will be same as the number of ways to arrive at node number 0, because this is the first time we are visiting it. So just store that for node number 0 we have one way to visit, and so it will be for node number 4 as well. We put 1 here. Now we traverse node number 6. So for node number 6 again we update the distance, because 7 is better than infinity, so we update 7 here, and we put 1 here. We put the number of ways to arrive at node number 6 will be same as the number of ways for node number 0, that would be 1. Similarly for node number 1 as well, it would be 2, because 2 is better than infinity and the ways would be 1. Now we have these 3 nodes into the priority queue. Node number 4 with distance as 5, node number 6 with distance as 7, and node number 1 with distance as 2. Now we can see that out of all 3 nodes, since we are pushing them into a min heap, this node will be popped out in the next iteration. So this will process this node, that is node number 1. So traverse its adjacent nodes, node number 3 and node number 2. So for node number 3, the distance that we calculate would be, the distance for node number 1 is 2, so 2 plus 3 is 5. 5 is better than infinity, so update 5 here for node number 3, and the number of ways to visit node number 3 will be same as the number of ways to visit node number 1, because we are visiting node number 3 first time. So it will be 1. Now move to node number 2 and repeat the same procedure. For node number 2, we are visiting it first time, so 2 plus 3 would be 5. The distance will be updated to 5, while the ways will be same as the ways to arrive at node number 1. That would be 1. Fine. And we also push these two nodes into the priority queue. That is node number 2 with the distance as 5 and node number 3 with the distance as 5. Now pop this node out of the queue, that is node number 4. So pop this node number 4 from the queue and traverse its adjacent nodes, that is node number 6. So for node number 4, node number 6 is the adjacent node, so update the distance for node number 6. For node number 6, the distance that we already have is 7, and here you can see that the distance that we calculate through node number 4 will also be 7. 5 plus 2 is 7. So it is not better than the distance that we already have. That means whether we come to node number 6 through this node number 0 or this node number 4, the cost or the time stays the same. That means these are counted as two ways. One will be just move from 0 to 6, the second will be just move from 4 to 6, and the number of ways will be the number of ways for node number 0 plus the number of ways for node number 4. So what are the number of ways for node number 0? It is 1, and the number of ways for node number 4, it is also 1. So the number of ways to arrive at node number 6 would be 2 at this point. So 2 is better than 1, so we'll update 1 with 2. Fine. So I hope you're getting. Now we have traversed node number 6 and we visited it second time. So we're not going to push it into the priority queue because we have already computed the best answer for node number 6, that is 7 units of distance. Now pull the next node from the priority queue, that will be this node number 2. So pull this node number 2 and traverse its adjacent nodes, that is node number 5. Now update the distance for node number 5. It would be the distance for node number 2, that is 5, plus the edge weight, that is 1, that is 6. Is 6 better than the distance that we already have for 5? Yes, we have infinity for 5, so we update the distance to 6. Also update the number of ways to arrive at node number 5. Since we are visiting node number 5 the very first time, the number of ways would be same as the number of ways for node number 2, and it is 5. So update the answer for node number 5 with 2 and push node number 5 into the priority queue. Update the nodes, update the distance for node number 5 to 6. Okay. So now out of these 3 nodes that we have, 6, 3 and 5, pull this node 3 because it has the shortest distance. Now for node number 3, traverse its adjacent nodes, that is node number 5 and node number 6. Now when we traverse node number 6, we are traversing it again. We have already visited node number 3, and if I visit node number 6 through node number 3, the distance would be 5 for node number 3 plus 3, that is 8. 8 is not better than the distance that we already have for node number 3, that is for node number 6, that is 7. So 8 is worse than 7. So this is not counted as the shortest path to arrive at node number 6. So we just discard this pair or this node. Now we traverse this node number 5. So let's calculate the distance to arrive at node number 5. So if I arrive at node number 5 through node number 3, the distance would be the distance for node number 3, that is 5. 5 plus 1 would be 6. And it is same as the distance that we already have for node number 5. That means this is counted as the another shortest path to arrive at node number 5. Fine, because the distance is same. So that means the number of ways to reach at node number 5 will increase by the number of ways to reach node number 3, because till node number 3 we have like some ways to arrive at node number 3. Now from node number 3 we can just move to node number 5. So whatever the number of ways are there to reach at node number 3 will also be the number of ways to reach node number 5. So just add the number of ways for node number 3 into the number of ways for node number 5, and that is 5. So we have 5 ways to, so that is 1. So we have one way to arrive at node number 3. So add 1 for 5 as well. So for 5 we would have 3 ways now. Fine. 3 ways, right? Yes, we have 3 ways because well, it's not 3, it would be 2 ways because one is from 0 to 1, then from 1 to 2, and finally from 2 to 5, and the second would be from 0 to 1, then from 1 to 3, and then finally from 3 to 5. So we have 2 ways to arrive at node number 5. Through node number 3 and through node number 2. Fine. So for node number 2 and 3 we have one way for node number 2, one way for node number 3. So we add them, that is 2, and that is our number of ways to arrive at node number 5. Now we pull another node because we haven't updated the distance for node number 5. We already have the shortest distance for it. So we pull the next node from the priority queue, that is node number 5. Now pull node number 5 from the priority queue, and from node number 5 traverse the adjacent node, that is node number 6. So traverse node number 6, and we can see that the distance to arrive at node number 6 through node number 5 would be the distance for node number 5, that is 6, plus the edge weight, that is 1. So 6 plus 1 is 7. Is 7 better, or it is the shortest path, or it is not the shortest path? Yes, it is the shortest path, because for node number 6 the shortest path length is of 7 units, and definitely it is one of the shortest path to arrive at node number 6 through node number 5. So add the number of ways to reach at node number 5 to the number of ways to arrive at node number 6, and that would be, there are 2 ways to arrive at node number 5, and 2 plus 2 would give me 4. So add 2 here, and this will give me 4. So we have 4 ways to arrive at node number 6 now, and we are not going to push this 6 into the priority queue because we haven't updated the distance array. Now pull the only node from the priority queue, that is node number 6, and for node number 6 the distance that we already have is 7, and this is indeed the distance, and this we can see is the destination node. 6 is the destination node, so we return the number of ways right from there, and we quit our while loop. So we return 4 will be the answer. So in this fashion we'll be solving this problem. All we had to do is just use one more array ways and keep adding the number of ways to arrive at any node by adding the number of ways to arrive at their parent nodes if we are arriving at the current node through the shortest path. Fine. So that's the idea. So let's just jump to the code implementation part. We just have to use one more array. There is no meaning in writing the pseudocode because the pseudocode is just the Dijkstra algorithm itself. Okay, so this is a solution class where we have a count paths function which takes in the 2 arguments, the number of nodes and the roads vector. Now here declare a adjacency list of pairs of size n and prepare this adjacency list from the given roads array. So we have bidirectional edges, so create bidirectional edges. Fine, so this is A, D, J. Now from here also declare 2 arrays, let's say distance array of size n, initialize it with 1e15, very large number, and a Waze array of the same size, initialize it with 0, initialize the very first node, initialize the Waze array for the first node to be 1, because there is exactly one way to arrive at node number 0, because we are just standing over that node. Now also initialize the distance array for node number 0 or the source node, that would be 0, and declare a priority queue. This is just the usual Dijkstra algorithm, vector of pair, or it's not vector, it's pair, and then vector of pair. Finally we'll have a comparator pair pq. Initialize this priority queue with the source node, so 0, and its distance is 0. Okay, the first element is the distance and the second is the node. Now also I am declaring another variable, let's call it mod, and it will be initialized to 1e9 plus 7, because we have to output the answer modulo this mod, because the output may be very large. Also we know that the edge weight may be large, so just use long data type for the weights. Also use long data type for storing the distance and the number of ways. So here I will be using, for the very first number I will be using long, so a priority queue of long int. Here also will use long. Fine. Now run the usual Dijkstra algorithm, that is run this priority queue. Pop the top element from this priority queue, that would be pq.top. Pop it from the priority queue and check if there is no scope for updating the distance. So we know the node is p dot first and p dot second, and the distance is p dot first, so long distance, it is p dot first. Now if the distance for this node that we already have in the distance array is better than this distance, that is dist, then continue to the next pair. Otherwise iterate over the neighbor nodes and for the neighbor nodes check if the distance for the neighbor node, so we have the node to which we are going, and the weight, that would be long. Now we have the neighbor node as well as the weight to arrive at the neighbor node. Now check if there is a scope for improvement. If the distance is greater than the distance that we arrive with this through this node, dist plus the edge weight, if it is the case, then that means update this distance array for the neighbor node, push it into the priority queue, new distance, and this node. Also here you have to update the Waze array, so Waze for the new node 2 would be, so here let me enlist two conditions that we encounter while performing this algorithm. That is, if the distance to the neighbor node to which we are moving while performing the Dijkstra algorithm, if it is greater than the distance that we have if we arrive at this node through that parent node, so and the weight, so this dist represents the distance to arrive at the parent node. Now if it is the case, then what do we do in the Dijkstra algorithm? So this, in this case where we are performing the relaxation, the distance at the ways array will be updated like this. Ways to reach at this neighbor node 2 will be same as the ways to reach at the parent node. That would be ways to reach at the parent node. Why? Why it is the case? Because we are visiting this node 2 for the very first time. Like here, when we were visiting node number 4 for very first time, the number of ways to arrive at node number 4 were same as the number of ways to arrive at node number 0, because we are visiting node number 4 as the adjacent node of node number 0 for the first time. That's the condition. Otherwise, if it is not the case, if we have something like, if the distance, so let's call it else if the distance w2, that means this is another path or another shortest path to arrive at this neighbor node. In that case, we simply count the number of ways to arrive at this neighbor node 2, and we increment the count by the number of ways to arrive at the parent node. So in this case, the ways array will be updated like this. Ways 2 would be like ways to reach at the neighbor node plus the ways to arrive at the parent node. Since we have to calculate the answer over this mod, so we mod it with this variable mod. So this contains 1e9 plus 7. So in this fashion, this ways array is updated in these two conditions. Finally, at the end, the answer would be simply ways to reach the last node, and the last node is n minus 1th node, and that's my answer. Fine. So let's just code these conditions. So here we just have to calculate ways to arrive at the parent node. Otherwise, if this is yet another path to arrive at the neighbor node, in that case, just update the ways to plus ways to move at the neighbor node mod. Fine. And at the end, return ways n minus 1 mod. Fine. So we return the answer right at the end of this function. So let's just try to run this code. Okay, it gave me positive answer, so let's submit it. So let's submit it. Okay, it worked. So that's all we have to do. The time and space complexity stays the same as for the Dijkstra algorithm. So that's all for this video. If you like the video, then hit the like button and make sure to subscribe to the channel, and stay tuned with me for more such videos and content on data structures and algorithm. So I hope to see you all in my next videos.